right, so we'll have a quiz next Friday. Next week we will have no lecture. No lecture on Monday or Wednesday. I'm going to be out at the ACS conference, and so I'm going to post worksheets for those 2 days and videos where I work the answer key. All right, so you should work those worksheets. And then let's see. So then I also want to bring to your attention that our exam 3 is going to be not Wednesday, but the following Wednesday. Okay, so please don't decide that because we're not having lectures that you don't need to practice this stuff, because we're going to have an exam. We'll have Friday, Monday. I'll give you a hack on Friday. We'll talk about titrations, then we'll do review on Monday, and then we'll have the exam. Okay. Let's see. I have office hours today, 1:15 to 2:15. As usual. And then next week I'll try to offer office hours. You can also say, hey, I want to talk to you on Google Meet or something. I'm going to be at this conference, but I'm not going to be 24 hours a day at the conference. So I can carve out times. I'll figure out once I get there when my times would be good, but I can probably carve out times at least in the evening where I could talk to people. So please take advantage of that. Questions on things we've got going in class? Okay, then what today we're going to do is we're going to talk about your author of your book has made up a new thing, I think. I hadn't seen this before in other textbooks, but he's going to put a fire table in front of the ice table, all right? I think he's a Game of Thrones fan, all right? So, but I decided I would use this anyway because it's a nice little thing to say, hey, these are two-part problems. You're doing one set of things, you're doing a set of stoichiometry things, and then you're going to go ahead and do your ice table. All right. Now I'm going to skip the ice table in these problems anyway because we have the Henderson-Hasselbalch equation. And pretty much whenever you don't have a zero for your acid or your base, you can do the Henderson-Hasselbalch equation. So let's talk about that really quick. So we've got our Henderson-Hasselbalch equation goes like this. All right, that's our Henderson-Hasselbalch equation, and we can use it for any of these sorts of problems as long as neither of those things is zero. If one of them's zero, like it's a problem where you start out with all acid or you start out with all base, then you have to use an ice table. Okay, so cannot be zero. All right, so we're going to go ahead and talk about what your author likes to call these fire tables. But essentially what's going on with these tables is if we're going to talk about what do you do or how do you calculate pH when a strong acid or a strong base is added to your buffer. Okay, and so an important point here is what we're going to do is we're going to assume that the strong acid or strong base reacts completely. Okay, and then you're going to then calculate new concentrations. Okay, this assuming it reacts completely. Calculating the concentrations is also part of stoichiometry, but this is definitely part of stoichiometry. Assume it reacts completely, then calculate the new concentrations. Okay, and then use new concentrations in an ice table or a Henderson-Hasselbalch equation to calculate pH. All right. Questions on that process so far? We're about to do it. Okay. This first one is just going to be about an ice table, though. Okay. Is it Haas, H-E-L? I'll have to look it up. That's how I wrote it last class. E-L? Okay, last class I was looking at, there we go. Okay, so last class I was actually looking at notes I'd copied. So what we're going to do here is we have a reaction where I've got a strong acid reacting with a weak base here. Both my acid and base are weak. So I've got a strong acid here. This was HCl, this was H2SO4, this was HNO3. Okay, something that's going to fully react. Make H plus here. But if I have this reacting with this is going to completely react, or it's react as much as it can, is maybe a better way of saying it here. So how would we fill out the rest of this table? Okay, so if I look at this, what I'm going to do is this is going to react as much as it can. I have 2 moles of my H plus, I have 0.5 moles of my conjugate base, so how much is going to react? 0.5, right? So you take for what can react, you take the smaller one. So this, we're going to end up with minus 0.50 moles, okay? And this right here, I'm going to end up with minus I'm not going to end up with, but I'm going to subtract 0.5 moles, okay? What do I do on the other side? What happens here? Add. For every one of these that goes away, I'm going to get one of these. So I'm going to add that. Okay? And then I'm going to go ahead and add my first and my second together. So this is where they get their fire. First, skip the I, reaction, then end. And so this is going to be 0. 0.5 minus 0.5 is 0. 2 minus 0.5 is going to be equal to 1.50 moles. Okay? And here, 1.5 plus 0.5, that's going to be 20 moles. Okay? And then they're saying make those into concentrations. All right, so let's go ahead and make those into concentrations. So you have 2.30 liters. Okay, so we've got the starting and ending moles here. I could actually take this pH and there'll be a little bit of this. We're just going to call it 0 for now. It's going to be, we could calculate it with an ice table. We're not going to do that. Remember that molarity is equal to moles divided by liters. It's not going away in chemistry. It's going to happen again and again and again. I'm going to scoot this up real quick. I'm remembering I've got 2.3 liters. Okay, so this one right here, for the acid, I'm going to have 2.00 moles in 2.30 liters to get my molarity. For this one right here, I'm going to have 1.50 moles divided by 2.30 liters. Okay, and so what did you guys get for what did you get for the H plus concentration? 0.65 molar, okay. And then what did you get for the acid concentration? 0.870. Okay. Is this a good buffer? It's not a good buffer because I've got none of this, right? Actually, I won't have none. I could do an ice table. I could find out a little bit what that number is. But essentially, I've got far, far, far less base than I have acid. All right, and so this can't go away anymore because it can't buffer it because there's no base for it to react with. What's the pH of this solution? So pH is going to be equal to the negative log of H plus concentration is equal to the negative log of 0.65 molar. You don't need to worry about the units so much. And then what does that end up being? 0.19, okay? So it's super low, right? Okay? So 0.1 molar acid is going to be, if it point molar 1 H plus is pH 1, and we have more than 0.1 molar. Okay? Questions? pH can even go negative. We've talked about that before. All right, so that's how we do that. And then if we had something where we didn't, we still had a buffer left over, we could have done Henderson-Hasselbalch to this or an ice table to figure out what the pH was. But we just have a lot, whatever small number this would be small compared to this, so our pH is going to be this, regardless of whether we figure out exactly how much base we have. Okay, all right. So now we're going to do that again, but this time we're going to do the whole thing, okay? We're going to have this problem right here actually has us, it has us figuring out what the concentrations are of everything at the end. So we're going to do an ice table. They say, I'm actually going to do a Henderson-Hasselbalch equation because I think it's easier. All right. But go ahead. First thing I want you to do is complete the fire table below. Now here's the tricky bit here. Let's see, maybe there isn't a tricky bit in this one. There isn't, okay? So just go ahead and fill out the fire. The next one has a tricky bit. So I'm asking you to do A, and don't worry about an ice table yet. And then if you get that done, go ahead and do B. And you're welcome to do C too, but yes?
The dash line means 0.
The dash line means 0, right. And in terms of the title, or in terms of the table, it's telling you up in the first line what everything is too, right? Where you start with. Yes.
So I just want to make sure I'm listening. This is on buffer, or this is on buffer?
Buffer is really baby sense confidence.
Dirty, that's where you're
Maskins come to face. Oh.
So.
Yeah, we don't yet have actually this. This is the face.
So why did we use 0.50 instead of like that minus, or like instead of that?
Why don't we use this? So that do it.
Like why did we use it all the way across?
These two things, I know we have too much.
Oh wait, yeah.
So.
Yeah, that's right.
Smaller numbers, that's much as we react. Those fully reacts, that's all the pluses. For every one of these that goes away, I need one of these.
Okay, that makes sense. Okay, thank you. So this one, it would be this. Okay.
Yes.
Okay.
Yes. Right. Which one do you subtract? You're gonna subtract the smaller or the two?
Okay.
Is that gonna be a addition?
Yeah. It's always the smaller. You might have to see it. I don't know if the books have do this. But
Yeah.
you could have slowed down.
Yeah.
Something.
Yeah.
I wasn't supposed to take it off, but one of the classes
I'll give you guys 30 more seconds here. And then we'll fill it out together. Okay, let's go ahead and look at this. So it doesn't talk about how much CL we've got, but we're not going to have any. I mean, up here, the CL's over here, right? okay? But it's going to break up to make Cl, so I guess that's why they left that blank. We're going to take the smaller of these two, right? This is going to completely react, which means not everything, not that they both go to 0, but they react as much as possible, so one is going to go to 0. And so all of this HCl is going to go away, and this is in moles, which is nice, because I don't have to calculate moles. We'll have to do it for the next one. But we've got 0, that much goes away there, and so for every HCl that reacts, I've got one of my molecule, my base, that goes away, right? Okay, and then for every mole, let's say, of base that goes away, I get 1 mole of acid, right? So this is going to be a plus 0.70. Does that make sense, what I just did? Any questions? Okay, so now I just need to add them up to get the end. And so I'm going to have 0.70 moles. I've got 0 moles here, and here I've got 0.70 moles. Okay, and now I have the moles of everything. So I want to look at what are the other questions here? Well, here, let's do B real quick. We're not going to do the ice table. We're going to do this with Henderson-Hasselbalch. But what I want you to, we are going to do this bit. Okay, so we're going to use Henderson-Hasselbalch to solve for those. But before we do that, go ahead and write an equilibrium expression for this base equilibrium. So that's going to be Kb equals, this is a base equilibrium. We have a base reacting. Actually, this is our equilibrium down here. This is what they want you to do. Do it for this one, not this one. Yes?
Why does Cl not have anything?
Why does Cl not have everything? Cl could have stuff. It just isn't important for us determining pH. So for every HCl that goes away, we're going to get 1 Cl, but it's a great question. And then we're going to have that much 7 Cl at the end. Okay, so how do I write this Kb thing? Products over reactants, right? So my products for this reaction, that's the base equilibrium equation, right? Because I have my base, this base is something that produces OH in water, right? So that's going to be the concentration of a drop of my acids, that's HC3, is it? C3H9N plus, I'm going to run out of room. Hold on. Yes.
In a second, can you scroll up so you can see the Kb?
Right. We're not going to use it, but okay. We're not going to use it yet.
Well,
Oh, you're doing. Okay, so you want to see the Kb. 5.6 times 10 to the negative fifth.
okay, thank you.
Huh? All right. So then we're going to come down here because I need more room to write this. And so our Kb is equal to, I guess since we're going to need it anyway in a minute, 5.6 times 10 to the negative 5. And that's equal to our products over our reactants. Our products are the acid, C3H9N plus. How do I know that's the acid? It's got a plus. It's more positive, right? That's one clue is it's more positive. The other clue is it's got an H in front. An H in front means it's an acidic proton, and the other one doesn't have an H in front. So those divided by my reactants, which is going to be my base. Why am I not putting in water? Because it's a liquid, and we don't put in liquids. Okay, so that's our equation there. Questions on how you set that up? Okay. Need to be familiar with those. Those are the base of what we're doing here. And then I'm trying to figure out what my OH minus and my H plus concentrations are. All right, so we're going to run a little bit out of room here. We're going to use Henderson-Hasselbalch to do this. All right. If I'm going to use Henderson-Hasselbalch, Henderson-Hasselbalch goes pH is equal to pKa plus the log of A minus over HA, like that. Okay. And so I need a pKa, but I've got a pKb or a Kb, right? So I need to turn that into a pKa. Anybody have a suggestion on how I might do that? Yeah. Okay, I'm going to turn into a pKb and then I'm going to subtract from 14. That's a great way of doing it. There are more than one way to do this as well. So I'm going to take the pKb is going to be equal to the negative log of my Kb. It's not a concentration. 5.6 times 10 to the negative fifth. I'm going to go ahead and put that in the calculator that I am used to using. And so I've got a pKb is 4.25, okay? And if you remember, our 14 is equal to our pKa plus our pKb, okay, is equal to 4.25. Not 4.25, sorry. So 14 is equal to pKa plus 4.25. That's pretty easy. I can subtract 4.25 from both sides, and I get 9.7. And now I can do my Henderson-Hasselbalch equation, right? All right, so pH is equal to pKa plus the log of A minus over HA. And so 4.25 plus the log of, and now I can actually just put in my concentrations from above, or my moles from above. All right. The reason I can do that is if we look at, these are in moles, right? What's the volume?
120.
It's 120.
I mean, 1.2.
1.20 liters for that, right? So let's look at that. So we've got 0.7 and 0.7. All right, I think I can remember that, maybe. You can remember that. Help me out. So, yes. Oh, thank you. Yep. 9.7, right? I put the pKb in there. Okay. So I've got this A minus over HA bit. I'm just going to pull that out on its own, right? Do you see if I put in 0.7 over 0.7, that's the same as 0.7 over, you said it was 1.2 liters? So that, it's moles. Remember, molarity is moles divided by liters. And so I have 0.7 moles and 1.2 liters, and the bottom of my 0.7 moles over 1.2 liters. They're in the same solution, so these are always going to cancel. I'm going to end up with the same ratio. Does that make sense? So if I have moles, I can use that directly in the Henderson-Hasselbalch equation. If I'm doing a Ka, Kba, or Kb equals something, that has to be in molar. But this way I can skip that part. So I'm excited about that. So this is going to be the log of 0.7 over 0.7, right? Because that's what those were. And so our pH, the log of this 0.7 over 0.7 is what? 1, and the log of 1 is what? 0. So my pH here is actually equal to my pKa. Okay, does that make sense? All right, and then the problem asked for the OH concentration and the H plus concentration. So we can do that. I know that my pH is equal to my pH, sorry, is equal to my negative log of H plus concentration, right? And so 9.7 is equal to the negative log of H plus. And then to solve that, I'm going to take the anti-log of both sides. So I'm going to take 10 to both sides. It's going to go better if I go ahead and multiply both sides by -1 first, right? So I get that. And then I have All right, I get my H plus concentration is equal to I'm going to go 2.0, I don't remember how many sig figs I have, times 10 to the 10th, right? Other people get that? Okay, and now I need to figure out my OH concentration. Remember that I could look up at the top of my test and get the number for KW, right? KW for water is equal to 14, 20 times 10 to the 14, which is equal to H plus concentration times OH minus concentration, right? And so I've got my H plus concentration now, 2.0 times 10 to the negative 10th times OH minus concentration is equal to 1.0 times 10 to the negative 14th. And then I can just divide this. All right, and that ends up being my OH concentration. So I divided both sides by 2.0 times 10 to the negative 10th, and that gave me 5 times 10, 5.0 times 10 to the negative 5th molar. Yes?
I don't know if maybe I'm just getting my sig figs messed up.
Uh-huh.
But with the 9.7, when you're doing that, should it be 9.75? Only because it gives you a very, not that much different, but a different answer when you put it up to 10 to the negative 9.75 versus negative 9.7.
So I'm trying to remember where I got the 9 points.
It's 14 minus
We had
4.2.
We had 2 sig figs there. Whoops. Yes, in terms of sig figs, we're working with 2 sig figs, and 9.7 is 1 sig fig. I agree with that. So let me remind myself how I got there, though.
14 minus 4.25 is when we had.
Yeah.
Because
So,
it gives you a significantly different answer.
Yes.
It gives you 1.78 times 10 to the negative 10 instead of 2.00.
okay. 1 point, what was it?
7.8.
Yeah, I agree. Okay. So did you guys hear that comment there? I dropped a sig fig here, and I should not have done that. Yes.
The 2.0 times 10 to
Mhm.
10, is that from where you got 10 to the negative 9.7?
Yeah, that's.
Yes.
Okay.
Yes.
Sometimes my calculator is messed up.
That's like,
Other questions? Yeah.
I'm confused. Are you doing 10 to the negative?
I'm doing 10 to the negative 7, 9.7,
Okay.
and that's how I'm getting this.
Okay.
And Terrence's correct, I should have had another significant figure. I think I'm not going to fix it unless people really want me to. Okay.
My calculator is not giving me the same answer as the 2.0. Is there a?
What is it giving you?
It's giving me, so I do 10 to negative 9.7. I'm getting 0.
Okay. So talk to me afterwards, or maybe on the next problem, and come over and look at your calculator. We can figure out how to make it do that. Okay. Other questions? So this, in terms of this problem, we were asked for this, and we were asked for that. Okay, so let's go ahead, seeing how to do one of these. Now, I wanted you to do this one. The tricky part of this one that's new, it's new in terms of what we're doing today. It's not new in terms of problems that you guys have had to do, is you're going to need to calculate the moles, right? Things react in moles, and so you're given 2 liters of this concentration and that concentration, right? Okay, and then you're also given, here it's different, you're given milliliters of this concentration. So I want you to go ahead and try and do that. Remember that molarity is equal to moles divided by liters. So if I multiply liters times both sides, liters times moles, or molarity is equal to moles. That's how you can get moles, right? So if I figure out the moles of this, I multiply 2 liters times that. And then on the way through. Keep in mind, this is milliliters, not liters, so you'll have to put it into liters, 1,000 milliliters in a liter. Call me over if you have questions. lots of questions last hour, so I'm sure you've got lots of questions and you're gonna get stuck places. And please call me over for help. Okay, well, look,
So, we need to start by calculating the fees for educators, right? So, can you do the illustration walk through? But we have to have. Take concentrations and make them. All of those in other questions? If you guys don't ask me questions, I'm gonna like get out my phone and text my wife about this decision that got made that I'm mad about.
Oh, that makes sense. Okay. I thought it was 12 more, like readers added.
Yes, yes, it's a lot.
So, the rule over here, you were saying you have to have them in rules. If we want to use this calculator, is that right?
No, we have to have goals to figure out.
It's not tied to volume.
Things don't react with the similarity. So you could use the 12.
Would be the first step.
So I got 2 liters, this much stuff. I'm adding that much stuff. It's concentrated. And so I don't know how many moles are in here. Couldn't react, not all of the concentration.
Okay, well, yeah.
Other questions?
So when you do this, the volume is gonna be the October figures, right? It's gonna be 2 plus the 10 values.
So you could, so give me the question again, hold on.
So I'm to the point with it where I'm finding the new concentrations of each. And is the new volume going to be, or is the volume gonna be 2?
The new volume is
gonna
gonna be 2.12, but you don't need concentrations when you solve this one. You just need moles, so you can figure out concentrations and do a nice table. Do a nice table with concentration.
Right.
But you're gonna need, I just go straight into, Anderson Hasselbalch with the moles.
Oh,
Because they're all, it's all the same volume.
no, that makes sense. And also, I had a question. So I understand that it gives it to the KD, but for me, it's a whole lot easier to set up the equilibrium expression for the acid and its conjugate base, and I just use the like I get a pKa from that. Is that going to be okay on a test or a quiz eventually? It's easier for me to figure out what the equation is supposed to be if I do a dissociation of the acid. Is it? Yeah, it's an
PKA.
there you go. That's great. All right, let's go ahead and look at this. So we've got a 2-liter solution, or at least do the calculations. I've got 2. Actually, let me write out the reaction. So I've got a reaction here, right? It's a Kb, so I'm going to write it as a base reaction. Which of these is my base? Is it the top one or is it the bottom one? How many people think the top? Okay, you just told me. So it's the top one, right? If enough of you said in unison it was top, great. So that's my base. It's a base reaction. So I'm going to have CH5H4N is going to react with water, right, to make CH C5H4N plus, Okay, I know that's my acid because it's plus, also it has an H in front and the other one doesn't, plus OH minus. Right, that's my base reaction there. Okay, and then so I need to figure out how much of stuff goes everywhere. And so I have, this is my fire, right? FRE. And so I start with, now I need to know what my moles are, right? So I'm going to do this one right here, and I'm going to just get the other moles from you guys. I'm going to do this one because it's a little more complicated. I'm low on sleep. I'm thinking about a decision somebody made that I'm mad about at the college. So I'm going to set this up and do it so I cancel my units so I don't make a mistake. So 1,000 milliliters in 1 liter. I cancel my units here and I get 0.010 liters. Okay. And then moles are equal to liters times mole or molarity. So I've got 0.01 liters times 12.0 molar is going to give me 0.12 moles. I was just doing this one. Okay. So I'm going to go ahead and where my HCl go? Oh, my HCl's, you guys need to help me on this sort of stuff. I've got my HCl is here, right? Sorry, I'm setting up the next equation there. That's what that should look like. Okay, so 0.12 moles. How many moles did you guys get for the base? 0.740 moles, okay, which is 2 liters times that, right, that concentration. And then what did you guys get for your acid? 1.100, lots of significant figures here, moles. All right, now we need to figure out how much is going to change. So our acid is going to react as much as it can. Which is smaller, this or this? Left or right? Right, okay. So we're going to end up with this, our acid's going to completely react, okay. It's also going to completely react with our base, okay. And over here, we're going to get for every one of these that reacts, how many of these do I get? 1, right? So I'm going to end up with plus 0.12 moles. All right. So this, I'm going to subtract. So my end, I'm going to end up with 0 moles of HCl. I'm going to end up with 0.62 moles of my base. And I'm going to end up with 1.22 moles of my acid. You guys agree with that? I'll fix my sig figs at the end. Sometimes get me in trouble with these pHs, though. I need to be more careful with that. All right, so now what was the question asking me for again? The final values of these things, right? So this is a weak acid, right? We got the KB up there somewhere. I'll look at it, but it was not big. Okay? So this is going to be we're not going to end up with much change here once we make these. So those are our final values. We can make that assumption. So part of our answer is what's the concentration of CH4N? And that's going to be equal 0.62 mole. Well, the concentration actually, we need to divide by, does it want the concentrations?
Yes.
Ah, okay. We're going to have to divide by the volumes there. Okay? So the volumes actually do matter. What's my final volume here? It's 2 liters, and then I add another 0.01 to it, right? So 2.01. So my final concentration of my base here is 0.62 moles over 2.01 liters. Shoot, I was hoping I wouldn't have to calculate it. All right, so I've got 0. How many sig figs do we have at the start of problem? 3. 0.308 molar. Other people get that? Okay. And then my final concentration of the acid, C5H4N plus, is going to be 1.22 moles over 2.01 liters. They're in the same volume. And so then that's going to give me 1.22 divided by 2.01, and that's going to be 0.607 molar. Is that what other people getting? Yes, Carolyn.
Where did you get the 2.01 liters from again?
That's a great question. Where did I get the 2.01 liters? I am mixing together 2 liters of one thing, and this we decided was 0.01 liters. Okay. And it is, since we're doing 3 significant figures, and that's 3 significant figures, it does matter. All right, so that's part of my problem. There we go. I got that credit on my problem. Now, I need to go up here and what's the final pH? Great. Now I'm going to use the Henderson-Hasselbalch equation. Okay. Now I'm given a KB which doesn't 8.77. So my KB is equal to 8.77. But I think above what we did is we did use the 14 rule, right? Already. So we know that 14 is equal to our Ka plus our Kb.
I think it was PKB.
PKB, thank you. Right? It's a PKB up here. So I'm going to use the PKB down here. And so that's going to be equal to 14. I don't know what my pKa is, but I know my PKB is 8.77. And now I'm going to be careful this time to keep all my sig figs. So I'm going to do 14. I'm going to subtract 8.77 from it, and I get my pKa is equal to 5.23. And now I can use my Henderson-Hasselbalch equation. pH is equal to 5.23 plus the log of the A plus over A minus, or A minus over HAA. So the base over the acid, right? And since I have concentrations, I'll use them. But I could have used moles. So 308 and 607. 0.308, 0.607. Okay. I'm going to go back and check because yeah, that was the acid. The acid needs to be on the bottom. 0.308 divided by 0.607. Okay. And I'm going to take the log of that, and then I'm going to add that to 5.23, and I get a final pH of pH equals 4.34. Questions? Okay. I agree with you. I mistranslated it from my calculator. Okay, this is why you show lots of work on your problem, because that would have been out of a 10-point problem, 2 points or 1 point when I was grading that I couldn't read my calculator. Questions? Not going to let you go early. I know, it's horrible. Maybe I'd let you go a little bit early. I actually ran over by a minute for the other class. The other class is waiting? Yeah. Okay. I want to talk real quick. I'm probably going to repeat myself on this because I didn't make it this far with the other class, but I want to talk about how do you know where a good buffer is? Okay? Yeah, I'm not over. Okay. You guys are confusing me. So we talked about this the other day. When is a buffer good? Okay, and we say a buffer is good when we have a decent concentration or almost equal concentration of the acid and the conjugate base. And that roughly equal is within, what did we say yesterday? Within 10 to 1 or 1 or 10 to 1, whichever way you're thinking of it, of each other. And we've talked about where those ratios land. This corresponds to 1 pH unit from the pK. Know the math on that. Okay, so I've got this list of a whole bunch of buffers that people might use to do biological stuff, right? To work in a biological system. And what I've got is let's scoot this down. I'm going to make it even smaller. Let's say, actually, my example this morning, I didn't look at this very carefully. I was saying, hey, let's say I want to work in the lysosome, I should say. Okay, so this is a list of pKs here. Can you guys see it, hopefully? No? Okay. Here's a list of pKs right here. Those are our pKs, okay? And what we'll do is we'll increase the view. The lysosome has a pH of about 4.7. Let's use these. Which of these buffers should I use then? Which of these buffers would be good? None of them, right. Okay, that wasn't what I meant to do this morning. But that's the way we're doing. None of these buffers would be good. I would want something else. Pick something else off the shelf. I'd have to order something else that had a pK that was within 1 unit of that 4.7. And preferably 4.7 straight on would be best. Does that make sense? Okay. All right, I am letting you out 1 minute early. Go by that clock.